Hi everyone. Welcome to the last session of today. I hope everyone got their drinks for the last session. I'm Ovidiu Hutuleac. I'm a solution architect here with AWS, based out of Munich. I've been working with the enterprise customers in the last couple of years. I was myself DBA in the past and more in data integration involved. So I'm looking forward to the session today and what are we doing from AWS side to expand the capabilities in the database section, right? So we're going to dive deep into a couple of database innovations that we did in the last year. We cannot cover everything. As you know, there are many database services on AWS. So the expectation will be to just go over a couple of new features and how they are working, so go deeper in those features. And then we're going to look at some relational database new features that we introduced, mostly on Aura and RDS. And the second part, we're going to look at some purpose-built database innovation that we introduced lately. And why we want to do that, actually, why do we want to deep dive in database new features is the way data is generated, actually, in the last couple of years, kind of changed the role of the DBA, right? So the database administrator or the cloud engineer out there who is taking care of databases is kind of disruptive of the way data is generated today. I mean, there are a couple of trends. Three of them I listed here. The data grows very fast in the last year and will continue to grow. And mostly are coming from, think about devices that are generated data. Think about all the new devices that are deployed out there. They are all sending data. We want to collect those data, this data to get more insights on that. And this is changing the way data is consumed as well. Because microservices that maybe were monoliths a couple of years ago and could tackle an amount of data generated per second or inserted per second, they are not scaling anymore, so they move more to a microservice architecture where you have different domains with purpose-built data stores. But these microservices as well, they generate also more and more data between them, like as interaction, and as well for the analytics afterwards. So for think about operational analytics, is getting more and more data, as well with the DevOps. So if you heard about the DevOps culture, how businesses can move faster, deploy faster in a secure manner, it's also increasing the rate of the change. The rate of the change increase means also more data generated, right? So if we dive a little deeper, so how is modern application requirements looking today? We are thinking about millions of users going global, scales up to exabytes, and needs to be super fast. So it's all about scalability, performance, and availability. And this is challenging, actually, for all the administrator out there, so the cloud admins and database admins, as well for the software developers that are trying to meet these requirements and scale performance and availability. And yeah, so what software developers and admins can do in this way. So they look at the traditional architecture and they think, okay, it's working fine up to a specific limit of, let's say, requests per second. And then we need to move. We need to move to microservices and do more decoupled services because we are not scaling anymore. We cannot meet the performance that we want only having one application. And this has also some implications because you're now thinking more in domain-driven design, right? So each domain has the full ownership given to a team. So the team developing that domain. And the full ownership means also how do you do compute, how do you get requests into the system, as well as how you store the data, how you manage data, how the data is flowing around. And this implies actually you have the ownership not only to choose the technology for the compute, you have actually the ownership to choose also the data stores. And that's why it's the trend that, in the last years that more and more databases are oriented not only to relational databases, but as well to purpose-built databases to meet those highly requirements. And on AWS, we have the most complete set of relational and purpose-built databases available for you. Why? Again, because the cloud admin and the database admin out there, they cannot manage all these DB agents by themselves. They need skill, they need time, they need resources to do that. So what we want to do is to make it for you easy. Make it for you easy to deploy new database engines like a managed service. Think about relational databases for RDS or for Aurora. As well, give you the possibility to, with the time that you won by not managing all the heavy lifting for relational, you can use that time and maybe ramp up on different DB engines like NoSQL engines, right? Great. Let's jump into the relational databases, right? The relational databases has been out there for the last more than 40 years, right? We have RDS. We develop RDS because customers told us it is hard to manage a relational database, so we developed RDS. That was back then in 2009. What RDS did was just automating the software development, the software deployment, not the development, and the patching, maybe the maintenance of the server, as well as giving the ability to have the storage with IOPS increasing as you need, the size increasing as you need. And it was really, really loved, but our customer said, but we want to scale more, want to scale fast. When we have our data, we wanted also to have it more available. What happens if that instance goes down? We need to migrate to another instance, maybe to another multi-AZ. So that's why we went a step forward and we look at the Aurora, right? So Aurora provision database, it's a cluster where the storage spreads over 3 availability zones, making the performance and the availability of your cluster much better, right? And then there were people being happy about that and said, yes, but what can we do with about compute part? We want to scale that as well and not just choose our instances as we need. So we took a step even forward and we introduced Aurora Serverless. And with the version 2 last year, you can scale now from 0.5 ACUs or capacity units up to 128, and the scalability happens in milliseconds. So you don't need to wait for another instance to come up and scale. This happens in place in milliseconds. Couple of releases that we had recently, right? So besides the Aurora Serverless part, we have the RDS blue-green deployment, so we're going to dive deep right away in that as well. The multi-AZ with 2 standbys, which has the ability now to create more than one AZ secondary for one primary. We have the RDS optimized reads and writes, which optimize actually your latency for the queries that you send to RDS, and we introduce also the guard duty for the RDS better protection to be more proactive in case of threats. And if you are a DBA or you are a DBA or an admin, you know how hard it is to do a deployment on a running relational database. I mean, there is locking mechanism in place. There are reading and writing already happening on the database. If you want to change the schema or you want to test some stuff directly there, it's pretty hard, right? So what we did, we think about in software development, there are already some best practices and how you can do the deployment of new features in a more secure manner, in a more, let's say, risk-free manner. So we borrow from there. We borrowed some things from there, and we introduced RDS blue-green deployments, which is also available for Aurora. But in this case, how it's working, we have a DB endpoint. DB endpoint which is pointing to current production, as you will do usually with a production database. Maybe have multi-AZ there or read replicas already set up. And just with a click on the console or the API call, you can create a green deployment. That's a copy of the blue, so a current production. And what we do behind the scenes, we're not only copying exactly the architecture of the Blue deployment, we also do the replication between. So as the data come into the Blue deployment, it will be copied also to the Green deployment. So you're pretty sure you have zero data loss once you are ready to do the switchover. And then you can do a lot of stuff here. You can add new tables, I don't know, modify the schemas, do some defragmentation, all these administrative tasks, let's say, at the table level or at the schema level. You can do that on the Green deployment, test it out, be sure it's working, and then again with the API call, you can just modify your primary to be the green one to be your new primary. And this makes actually your deployment, it's reduced actually the risk of deployment, reducing let's say the risk of unavailability of your service, as well as kind of incentivize experimentation, testing, and new features with risk-free. Great. Then we have Aurora, and we love Aurora. And I think you should too, because Aurora was designed with scalability in head, right? So we wanted to bring an open source engine to be scalable, like enterprise-grade scalable, and without licenses, so you pay as you go, and to automate it in a way that you not only the storage grows, so the storage is already decoupled from the compute, but the storage grows and shrinks decoupled, so separately from the compute part. And this is we still add new features to Aurora. We still look at the feedback of the customer to add more and more features, so we make it more easy for you and still increase that scalability that we want to offer with Aurora. How is Aurora working? So behind the scenes, we have a cluster storage volume. This cluster storage volume, once a request is sent, the cluster storage volume saves actually the data in 6 copies behind the scenes, and is doing this all in parallel. The 6 copies are across 3 availability zones, so you have highly durable and performant, let's say, data saved there. And then we kind of group those changes or data into protection groups, we call it, where it's like 10 gigabytes protection groups. And we save those protection groups on different storage nodes to increase, again, the durability and performance of the database. You can scale the storage up to 120 terabytes. It will scale automatically, so grow, and will shrink also automatically in case you don't need it. And this has some implication as well. We didn't want to have like a slow deployment of all 6 copies. So what we thought, we're going to use a quorum model. So you send, for instance, a transaction to be saved into the database, and it will send to all 6 storage nodes in parallel. Once 4 of them are responding with acknowledge, yes, I have the data persisted, it will come back to the database instance and say, I have persistency, nothing to do more, and database instance can go forward with a quorum of 4 out of 6. And behind the scenes is self-healing. So if a disk maybe is failing, or maybe some of the let's say of the storage nodes don't get the change right or is corrupted, so it's self-healing behind the scenes. You don't need to think about grabbing new disk or moving data around or let's say doing corruption healing, because behind the scenes we take care of that. And it has also an implication on the tolerance. So we tolerate 2 copies down. So even if a full availability zone, unlikely event of full availability zone going down, you still have 4 out of 6 copies, and you can move on with your database. On top of that, we have our writer, and we have up to 16 read replica that we support on that. And the interesting thing is, the readers, they are reading from the same storage, like the writer. So they don't have like different storage, and we replicate there the changes from the writer. Everything happens in the same shared cluster volume. So we open up the MySQL and the Postgres engine, actually just setting 1 parameter. So we open up read-only and the read replica. And at the end, the writer and the reader, they are reading from the same storage. How is this possible behind the scenes? Because it's not only scalable, it's also very performant. So one thing I didn't mention about the storage is the storage is a log-structured storage. So this is not a classical block row storage in Aurora, it's a log structure. This means the database engines, MySQL and Postgres, they are only sending to the storage only the logs. So they don't send the whole pages and the logs and all the other, let's say, writes that the database engine is doing. It's only sending the logs. Behind the scenes, it's working like this. So we have always 6 storage nodes available for one, let's say, from one write. The database instance is sending the log changes to 6 storage nodes in parallel. And what happens on the storage node, if you go a little deeper, the logs are put in a queue first, and then once they are saved into the hot log, so we are sure that on the storage node we have the change, we already sent the acknowledge back to the database instance. So database instance doesn't need to wait until we sort out the logs, or we see if it's missing something, or we build up the data pages. This happens actually asynchronously at the storage node layer. So this makes actually database instance much faster because there's less ping pong between databases and the storage, and there is also less data sent over the network. And it's part of the work that the database engines did before, like building up the data blocks. It's happening now at the storage layer. Behind the scenes, of course, we are doing organizing the records. We identify the gaps in the logs. So for instance, if something is missing, we gossip from another neighbor storage node, and we get that. We coalesce the log records into a new page, so a new page version. And of course, we do continuous backup also to S3. So we target in 0 data loss there, as well as doing some garbage collection and doing some validation on the blocks to make sure that the data, what was coalesced, and the page version that are there are not corrupted, for instance, right? Great, this is how it's working behind the scenes. And with that, we have also the ability to make the storage also dynamically resizing. So for instance, in this example, I maybe add a couple of new partitions every hour, so the storage usage goes up, as well as my allocated storage that I pay for. And maybe I drop and I create again, so the storage usage doesn't go up or down, it just stays the same. I have a 2-hour spike, maybe some batch system, some flash sale is happening, so the storage goes up automatically and grows with the need. And then maybe I drop those partitions or the data that I don't need anymore. So what will happen? So my usage goes down, the usage in the database. And if you're coming from traditional database administration, you know that the usage of the database stays the same. You still pay for the allocated storage, right? So this is like 2 extra storage costs that we don't like. We don't want to do that to our customer. So we implemented actually as soon as the used storage in the database goes down, we shrink as well the storage behind the scenes for you. So you only pay exactly for what you need. So this is what I meant about storage being dynamic resizing, growing and shrinking automatically. And you can take this storage and do other features. So for instance, think about our global database. It's not easy to do replication between multiple regions. I say it from experience, but with our global database, we implemented a solution where you can take a cluster from a region, so in my example, Ohio, and you can replicate that cluster up to 5 different regions. And we do that not with the bin logs of MySQL, for instance, or the WAL files from the Postgres. We do that at the storage layer. So we take the changes that are incoming into the writer cluster, and we replicate that behind the scenes over the AWS backbone network. So the changes are coming to us into another region, and we target actually most of the time under 1 second replication lag. It is working up to 200,000 writes per second. That's very hard to achieve actually with logical replication, but it's possible if we have this storage replication actually we do behind the scenes. And there are many use cases. So one of use cases could be like, I have my application. My application is running in the primary region. The primary region maybe has a writer, maybe a couple of readers, which are scaling up and down. The storage is scaling, all nice. But now if I extend my business, for instance, into another region, then it may be hard to move the application also there and still stay consistent, right? Because there are two applications. So what you can do, you can move the reads to that new region, for instance. So in this case, I'm moving to Ireland, for instance. But I can now move my application also there together with my read-only replicas, because if I use the write forwarding feature, I can not even read. I can read the data from the read replica, but I also can write to it with the write forwarding. And there are 3 read consistency parameters that you can set when writing into the read replica in another region. You can say, I want eventual consistency. So this means queries that are happening in the secondary AWS region, which they use write forwarding. So they will forward the write to the write region. They don't see actually their changes very fast. It's eventual. Eventually, it will be replicated to our read replicas. You can choose session level consistency, so you will see the changes that you did in your session, or you can do global replication, where actually the session that is writing into the read replica will wait until the changes are applied on the primary and all the other replicas. Right? So you can choose between them depending as your business requirements need. And again, you can do the third region, for instance, if you want, up to 5 regions. Another interesting use case, it's the serverless, and we have the V2. So we released version 2 last year. The main change between the V1 and V2 is actually that the V2 now is scaling in place. So in V1, we always scaled automatically also your serverless instance by moving to a bigger instance, right? So it's always like X large, 2X large, 4X large. So what we did with V2, we are adding CPU and memory to your virtual machine there directly in place. So this happens in milliseconds, and we are able actually to scale your instance with no impact actually on the running transactions that are happening already in the instance. So think about Lambda, right? So we have serverless architecture, and this is really dynamic and flexible, right? Maybe you have one Lambda calling now, maybe you have a couple of Lambdas later, so it can be really spiky. We need that data store to scale as well with the load, right? And so we're adding more and more compute and memory to existing database, so they can respond to the new requests. And once it's done and we have less, we can just shrink it back, right? So pay exactly for what you use. Let's take an example. Where can we use that? So think about performance insights. So you have a load like this, and you say, looking fine. So if I'm looking in the middle, I'm making a zoom in now there to see I'm like 58% now of the CPU. I'm okay. I'm using like, I don't know, total DB load is 9 out of 16 CPU. It's okay, it's no problem. But if we make like a zoom in there and we go deeper, we may see actually that was an average, right? So there was an average sampling of the last 5 minutes. If you go deeper, you may have these spikes, maybe for a couple of seconds, maybe for 10, 20, 50, 30 seconds. And those spikes are introducing latency in your application, right? You don't really see that if you don't go really inside. That's why it's challenging to see that. Where is actually my latency, increased latency coming from? So that's one area where if you're moving, for instance, to DB serverless, it will be able to add CPU and memory on demand as you need there. And looking at the right one, we are thinking more, when you see blue, it's more about reading. So maybe we have a session or we have a batch process there who's trying to read a lot of things from the database. And it's blue because it's waiting on the disk. So this may be like two things. What's happening behind the scenes? Either I'm reading a lot of blocks which are not already in memory, so I need to read it from the disk and they'll be cached. Or maybe I read them from the memory, but I don't have enough memory to keep the blocks for the whole transaction, right? So it's going up. I mean, CPU utilization is still up, but if you look at the latency, actually it's going like 10 times up. And it's challenging because you cannot see it directly from an IS, from average active session. You need to go deeper, and you need to understand actually where's the time spent there. And this is, if you go just a little deeper now into what's happening, you have those spikes there. Maybe someone is reading from a data file. So you have weights there that are going over the allocated CPU. Now we have 16, for instance, for a 4X large, like 16 CPUs available. It's going up. Everything that goes up there means increase in latency, increase in weights. So this is where serverless can help. I mean, if I move to a DB serverless instance, the load, once the load increases and the blocks, let's say, were already read into the memory, the serverless increases as well the CPU and the memory allocation. So afterwards, I'm just reading from the memory the blocks that are already there, so I don't go to the disk again. Great. So this has, at the end, reduced in latency about 8x in the experiment I did. But it's not really visible, as you can see. You need to go deeper and understand what is actually happening there. Behind the scenes, we already do that in serverless. We resize the buffer pool automatically for you. And there's a rule. Generally, we allocate around 75% of the memory for the buffer pool. So this means your blocks will stay in memory up to 75% of the memory available. But if we add more CPU and more memory to that instance, we are modifying behind the scenes as well the size of the buffer pool, so you can accommodate more blocks. So think about the algorithm, how actually the buffer pool is working. We have a recently used algorithm where the most read blocks are hot, so they will stay to the right in the queue, and the cold blocks will just move to the left as we expand our memory. So once we read new blocks, like we saw that in the blue weighting, new blocks will be inserted to the memory, like they will be used, and they will go to the right if they are most used, actually. So you can accommodate more reads from the memory as going to the disk. And this happens as well if we shrink the memory. So if you go down, if you don't have enough, maybe so many requests, we kind of evict the blocks which are on the left, so not really used. Then we shrink the memory. We reduce actually your cluster, or the ECU allocated, so you can move actually forward with the setup. Great. Behind the scenes for MySQL, there are a couple of parameters that we change. We look at InnoDB buffer pool size, for instance. We're looking at the max connection is also a thing, so it will be increased or decreased depending on how much memory and CPU you have allocated. And the same happening with the Postgres. So we have the shared buffers and some other parameters behind the scenes. You can see that in a default parameter group. If you go to Aurora and create a serverless, you have a default parameter group. Some of them have those really long formulas, so we do that behind the scenes. And another advantage that you need to know maybe as a database administrator, you can use now provisioned cluster together with serverless, so it's a mixed configuration. You can put, for instance, your primary on a provision cluster. Maybe it's a 4x large, and you know that's the baseline. But you can add as well serverless readers. You can put a serverless reader, maybe you have a BI team that is reading only in the morning or in the evening, as well as having other provision cluster for other teams as a read-only replica. And this is dynamically resizing actually the serverless as you need. All reading from the same cluster volume, like I said. So no need, even if you do a failover, you do a switch between the provision and the serverless, it will take just a couple of seconds to accommodate that because everyone is reading from the same cluster shared volume. Great. Now, let's suppose you already know all the innovations out there. You know, I did my best with my relational databases. I use a lot of features that are making me more performant, more scalable. It's time to look around the corner, right? So it may be that in your use case may have parts of the application that are not scaling very well at a specific limit in a relational database. So you look around the corner and you think, yeah, maybe I can I have a read-intensive application, maybe part of application that are really intensive read. Maybe I can use an Elasticache for that. I would just put a memory, in-memory Redis database in front, and then the reads will be much faster. So I kind of offload the database behind the scenes. So I need to read from a database. I read directly from the memory. The same, maybe I have one application which is just inserting a lot of just key values data. I would just look at the DynamoDB for that. We don't need relational databases for that. The same for the other, I don't know, document type data sets, or let's say Neptune, which is our graph-oriented database. And for those non-relational data interaction, we also released a couple of new features. So we are looking now, for instance, in the memory DB to add data tiering. So it's available. It's available now. We have for DynamoDB not only the export to S3, but also you can import data now from S3. So this makes it really easy to move data around from Dynamo and share it with other services that you may need. For the Neptune, we added global database and serverless. Kind of the global and the serverless is the new normal now for all data stores. And for Elastic, for the Amazon DocumentDB, we added Elastic clusters lately. So we're going to dive deep in each of them and see what actually changed and how can you use that. So Amazon MemoryDB, it's our service based on Redis that not only stores the data in the memory on one node, but it stores that actually over 3 availability zones. And it makes the data a little more persistent, so more secure for you. So you can add, you can have a client, for instance, that is sending a request to the primary. I want to store data in Redis. This will be actually behind the scenes stored in the storage in the memory storage, and then it will respond in a, let's say, with acknowledge that transaction. But behind the scenes, actually, the replicas are also getting that change, right? So this is kind of persistent data store in memory in case a failover is happening. So the primary may not be available. You still have your secondary that will take the primary role, and it will still make your data available for your application for the in-memory data. So we added the data tiering for R6GD instance types. So this means you can save the data not only in memory on those types of instances, you can also save that data on the disk, so local SSD disk, also in an LSU manner, so less recently used, where you have like the cold blocks, they are sitting on the SSD disk, and the hot blocks are sitting in the memory, and we do that automatically behind the scenes for you. You can accommodate like that more data actually in the same instance. Great. Looking at the Neptune. Neptune is our graph database, if you know. It has a similar structure over 3 availability zones. You have a writer, you have up to 15 read replicas on top. So what we added now, you can take that Neptune database, which is a graph-oriented database, and it will be replicated to up to 5 regions. So similar to other services that we already have there. And this makes really easy. It's not easy to find people with skill that know graph database engines and can do regional replication, right? So just use it if you need it in a regional setup, and you forget about it. You don't need to maintain this replication behind the scenes. The same happened with the Neptune on the serverless part. So we added now the capability to add DB serverless instances to Neptune. So you don't care about provisioning how much CPU do I need for that instance, how much memory do I need for that. It's going to scale up and down based on your requests, number of requests. DocumentDB. So DocumentDB is our document database on AWS. It's having a primary and read replicas also reading from the same storage behind the scenes. And this makes really scalable, again, makes really performant, and this makes also available in case the primary is not working. You can, it will automatically fail over to a secondary instance, and it's a very fast failover, so increases the availability for you. So this is the cloud-native architecture of DocumentDB. What we added now is the ability to build elastic clusters. And the elastic clusters are coming because we want, again, to scale more. So not scale only vertically, so add bigger instance, for instance, as well scaling horizontally. So we have the ability now with the addition of the elastic cluster that your application is still sending the data to the same endpoint, and together with our request router service, we can send actually the data to a specific shard behind the scenes, and each of the shards that are deployed there, they have their own storage and their own compute behind the scenes. So each of them are scaling actually independently from compute and storage, and independently from each other into the shards. So no instance or infrastructure to manage. It's more automatically done behind the scenes by the elastic cluster architecture. Great. Now, we went over the relational databases, and we saw already the purpose-built databases that are out there. But if you look now more into the industry, there is a paradigm shift happening, right? So the database admin, or let's say the owner of the data, or the data architect, it's really challenging to keep up running relational databases on VMs when you have so good managed services out there that can do the job. So the paradigm shifts is going in the direction of data admins expanding actually their knowledge, going not only to relational databases, but also want to develop new skills, how non-relational databases are working, how different data modeling techniques are working, and this is adding more and more value actually to your companies, because having a broader skills of data modeling will help different teams to build more successful and more performant application. And furthermore, at some point, it was for me also in the past, as was a DBA, the responsibility of a DBA is kind of expanding now. It's not only running my database and running well, it's also doing that data integration with other teams, or prepare actually that data for moving, for data engineering, for transformation in the future. And it's a good chance, for all the database administrators out there, for the cloud admins, that they can expand actually this responsibility and have more impact in their organization as before. So let's take an example. So if you're data admin and you're taking care maybe of one database and you have one application, let's say hotel booking application, right? So we have some pricing, some rooms there. We have a search team. We have a team that is doing maybe billing behind the scenes, and we have maybe some guest or preference or recommendation engine behind the scenes. We cannot put that everything in one relational database, right? It will not scale at some point anymore. So cloud admins, database admins are thinking now in domains. This is how the software development is also thinking. And in domains, each domain is taken care of by a specific team who has full ownership, not only of the compute, but as well as the data. So you can talk actually directly with those teams and understand what their requirements are so you can best data model their use case. And if we take an example, we could use that hotel booking to build actually free microservices, right? On one side, maybe we have the pricing, which just another create and push new prices. We can use a DynamoDB for that behind the scenes. There's another team maybe doing search. It's not easy to do search in DynamoDB, but you could use the streaming of DynamoDB to push the changes as they come into an OpenSearch cluster, and then you can do advanced search queries there. So it's a purpose-built service for what is needed for search. And the same, for instance, for user requirements. Maybe you have like a DocumentDB there where you have your user profile being flexible to add, remove history stuff or different attributes. If we make a step more behind and look at the whole organization, actually the database admins and the cloud admins, they think more in a data strategy way, where data is generated on one part. It can be application, can be operations, and I'll store it. But the story doesn't stop here. The story goes forward because the data will be modified. The data maybe will be transformed, and then the data will be integrated with other applications so you can serve insights generation, you can serve machine learning models on top of that data, and serve actually the people in the downstream application that are based on that. So you can take at the end better decisions actually. So our ongoing commitment goes in the direction of choosing the right tool for the job. To be honest, I didn't find in my last 20 years of experience an ideal database that can do everything. So there's no ideal database out there. Find the best tool for the job. The new normal is serverless. New normal is operation excellence. And the new normal is also going global. So we try to accommodate that in all of our services, as well as not only trying to bring the best services out there, but make them operate with each other the best. So I'll be here for another 5-10 minutes for Q&A. Don't forget to get us feedback in the app. And yeah, thank you everyone. Have a nice summit. Yes.